The subject of this lecture is time delays. Mathematically, a time delay is really just a translation in time when we say that a function has a time delay. So geometrically, what a time delay does is shift a function to the right. So if you can imagine a function f of t right here, so let's say it looks like this. It's the shape of a triangle. Okay, and then over here has slope 1. All right, let's say this is your function f of t. And if you introduce a time delay to this function, let's say a time delay of theta, let's shift it over by 2 units. Okay, so this distance here is theta. We're going to shift it to the right. So now the function will start here and still have this slope of 1 right here. And this would be your function with the time delay. This is f of t minus theta. Okay, so if we introduce a time delay, geometrically we're shifting the function to the right. So this function, the blue function, f of t minus theta, it takes on the same value that f of t took a time theta in the past. And to see that, let's consider at time t equals 0. So if we let g of t, this is our function of time, be equal to the shifted function f, shifted by a time theta, then g of t equals theta is equal to f of 0, right? And so that shows that the time delayed function takes on the value that the non-time delay function took on a time theta ago, okay? And you can also see this geometrically, right? So right here, if you step back in time theta, the time delayed function took on the same value that f of t took on a time theta ago. Okay, and you can do the same thing here. So at the apex of the function, you look back a time theta ago, and that's what the shifted function takes on. So you can see it both geometrically and algebraically here. In chemical engineering, time delays often arise because we deal with fluid transport in a pipe. So here's our pipe right here, and fluid is flowing through that pipe with a certain velocity, v. And L is the length of the pipe. And let's assume plug flow, meaning that there's a packet of fluid here, and this packet translates along the pipe. There are 2 concentration analyzers here, or composition analyzers. The first is placed at the beginning of the pipe, the second at the end of this long pipe. They're both identical composition analyzers, and they're both measuring the concentration of, say, salt inside this pipe. Okay? Now, there's a time delay here, and the etiology of this time delay, and etiology is a fancy word for cause, is that it takes time for fluid to travel from the first to second composition analyzer. So that is the etiology of this. It takes time for fluid to travel from first to second composition analyzer. How long does it take a packet of fluid to travel from the first composition analyzer to the second one? This is a little exercise in unit analysis. So the velocity is meters per second, right? And if it's traveling at a constant velocity, which would be the case if the fluid is incompressible and this is a steady state inviscid flow, then the time that it takes to travel from this composition analyzer right here to this one here is L over V, right? And I'll write in gray what the units here are. Meters over meters per second, and you get seconds, right? And this equals, and we'll define that to be our time constant, or our time delay. So that's how long it takes to travel. And so because of that, the composition analyzer 1 reads the concentration, the same concentration that this first composition analyzer, so we'll call this composition analyzer 0, saw a time theta ago. And here theta is equal to L over V, the time it takes for fluid to travel from C0 to C1, right? Basically what I'm saying is that the composition analyzer here sees the same packet of fluid that this composition analyzer saw a time theta ago, because that's how long it took that packet of fluid to travel from here to here. And so mathematically what we would say, we would relate what the concentration is being read from these composition analyzers, and we would write that C1 of T, right? That's the concentration output by this composition analyzer, right? Is equal to C0, but time delayed, right? Of T minus L over V, right? And so this is the time delay then, right here. So this is your time delay. Right? And so basically C1 takes on the value that C0 took on a time theta ago, which makes sense, right? And I'll highlight this with a different color. Right here, right? So that's a very straightforward example of a time delay. So I'll write this down. i.e. analyzer 1 reads concentration. Analyzer 0 read L over V time ago. Okay, and I'll highlight this to make this consistent. Okay, so that's a very simple example. So now what happens whenever we have time delays in our system and we need to take the Laplace transform of them? So let's go back to drawing an example function. Let's draw f of t. Let's draw some function, and let's say it looks like that, okay? So this is your function f of t. All right, and now we consider this function, we introduce a time delay. And we'll use blue like we did above. And I'll introduce a time delay of theta. So basically this is shifted to the right by, let's say theta is 2 here, okay? And then looks something like that. So this is shifted to the right by theta time units. So this is theta, right? And this needs to be theta 2, right? So if I copy this, I know if I drew it correctly because that has to be theta. So I'll put this in here to guide me. So that needs to go there, okay. All right, so this here is f of t minus theta, right? And what we've done is we've pulled the green function to the right, and we've brought the t less than 0 component with it. And remember, this is just a reminder that when we take the Laplace transform of a function, it ignores f of t for t less than 0. So what we need to do is assume f of t is 0 for t less than 0 anytime that we are taking the Laplace transform of functions. And so what we should really do is consider f of t times s of t as an input, where s of t will flatten the function for when t is less than 0, where s of t is the unit step function. And so this just emphasizes, well, your function f of t, we need to assume that it's 0 for t less than 0, okay? So what we're really doing is taking the Laplace transform of your function shifted to the right and also multiplied by this step function to flatten it for t less than 0. To figure out what exactly this Laplace transform is, let's go to first principles and write the definition of the Laplace transform. So we'll just put that function in there. This is f of t minus theta, s of t minus theta, and then we hit it with an e to the minus st dt, right? This is the definition. And now, this step function here, this is equal to 0 if t is less than theta, right? Because when t minus theta is less than 0, this function is going to be 0. And it's equal to 1 if t is greater than theta. All right? And because of that, what we can do is drop the step function and take into account the fact that the integrand is 0 for t less than theta. So we can write this as integrating from theta to infinity, because 0 to infinity doesn't have a contribution, f of t minus theta, e to the minus st dt. And what this is screaming for is a substitution. So let's let u defined to be t minus theta, okay? So that implies that t is equal to u plus theta, and it also implies that du equals dt, because theta is just some constant here. So this is equal to integral. Oh, and let's think about the limits too. So if t equals theta, that implies that u is 0. And as t goes to infinity, that implies that u also is going to infinity. So we can rewrite this integral 0 to infinity, f of u, e, and now this minus st term becomes minus s u plus theta dt. Whoops, and not dt, now it's du, right? So the e to the minus s theta term is not involved in the integral, so we can factor that out, right? So this is equal to e to the minus s theta integral 0 to infinity, and we get something very nice. What we get is the Laplace transform of f of t, but it's written in terms of u now, right? So this right here is just the Laplace transform of f of t. That's the Laplace transform of f of t, right? Doesn't matter if we use t or u, okay? And we'll define that to be capital F of s. And so what we've just shown is that if you take the Laplace transform of a function shifted to the right, where there's a time delay, then it's e to the minus s times the time delay times the Laplace transform of that function if you pretended it didn't have a time delay, okay? So this is a nice formula for deriving the Laplace transform of functions with time delays. As an example, let's consider a rectangular pulse input. I've defined it here. So the rectangular pulse input right here is m if 0 is between t and theta, and it's 0 otherwise. So basically, the rectangular pulse is m, and then after a certain time, it drops off, okay? And it's 0 again. And this value here is theta. This value here is m. So interestingly, we can write this in terms of a step. It looks just like a step function, right? Except what you're doing is subtracting off a step function that's shifted to the right by theta, right? And what that will do is you're subtracting 0 in this region, but then you're subtracting 1 from here on, and then you kill off that step function on the left. So this is t minus theta, yeah? And now we can take the Laplace transform of both of these, right? So the Laplace transform of a step function, Laplace transform u star of t, equals the Laplace transform of a step function, and we'll put that up here. So the Laplace transform of a step function s of t, and this has a, I'll put a little m here because, well, I'll put the m out front here. So it's times m, right? Because that's the magnitude, it's m. So the Laplace transform of a step function, a unit step function, is 1 over s, right? So this is equal to 1 over s. And then we have the Laplace transform of a function that's shifted to the right, of a step function shifted to the right. And what we have from this formula is, oh, well, we just pretend the function is not shifted to the right. So minus 1 over s. And that's its Laplace transform, that capital F of s. That's the Laplace transform of the step. But then we have this factor associated with the time delay, e to minus theta s times m, all right? So, and finally, that is the Laplace transform of a rectangular pulse. So it's m over s, 1 minus e to the minus theta s, okay? So this is one area where we use our knowledge about functions being shifted to the right and how that affects their Laplace transform. So you could get the same thing if you do a brute force integration, right? So you could put the function here, u star of t, e to the minus st, right, dt. And then what you would see is this is actually from 0 to theta, where there's where the integrand is valid, right? dt, right? And then you would get the same thing, well, times m. Okay, and then you get the same thing, m over s, 1 minus e to the minus theta s. Okay, but that way is not as fun because it doesn't use our newfound knowledge on time delays. So that's an example of you take the Laplace transform of a function that's shifted to the right. You just have this factor that pops out, e to the minus theta s. Now, what about when we want to invert Laplace transforms? Okay, so now we're taking the inverse of a function that involves an e to the minus theta s term. And anytime you see an e to the minus theta s term, what that means is there's a time delay. All right. And based on this, we just work backwards what we've derived. So if the Laplace transform, so I'll make it gray here. So this basically says that if you take the inverse of what we've derived right here, e to the minus theta times s, f of s, then this is equal to, if you invert that capital F of s, shift it to the right, hit it with a step function shifted to the right as well in order to flatten it for t less than 0. Well, for t less than theta, actually, to account for the fact that f of t for t less than 0 is 0. So we can directly, straightforwardly apply this to invert any expression in the frequency domain that involves this e to the minus s theta term, which arises from a time delay. All right, so to give an example, right here. So this is the Laplace inverse of e to the minus 2s, so theta is 2, 1 over s plus 3. All right? So this here is our f of s, right? And we know that f of t, which is the inverse Laplace transform of capital F of s, this is 1 over s plus 3 is the Laplace transform of an exponential, right? So this is equal to e to the minus 3t, right? So we know that. And so what we do is we shift this function to the right, okay? Because this is equal to f of t minus theta times s of t minus theta. So we shift this function to the right, e to the minus 3, and instead of t, we put in t minus theta. So t minus 2, right? And then we're not quite done yet, because think about it, this function, this function f of t, it's actually assumed to be 0 for t less than 0, okay? And so what we're doing here is we'd be bringing in the function for t less than 0 if we don't multiply this by a step function, which will make sure that the function for t less than 2 is 0, okay? And what we've done now is just taken the Laplace inverse of this expression here, and we're finished, okay? And so we'll often see these expressions whenever we have processes that deal with time delays. So let's look at a concrete process that has a time delay, okay? So let's do our familiar saltwater mixer. So what we have here, well, there's no salt flowing in, so this is a bit different, but what we have here is salty water, and it's coming in at a rate q. Flow rate q, and the incoming salt concentration is Ci, and I want to emphasize that this is a salt concentration right here, okay? So here's your little salt analyzer. So this is your salt composition analyzer. All right, and it turns out that there's a time delay here, right? There's a time delay of theta. So time delay of theta. And that time delay is associated with the time it takes for fluid to travel from the salt composition analyzer into the tank. All right. And so a mass balance on salt here, this is our system, right? So this is our system. This is our control volume. The accumulation in our system is V, and let's say the volume is constant, dc dt. So C is the concentration of salt inside that tank. And what's going out, we'll do what's going out first, is minus QC, right? That's what's going through the system boundary. Now, I want to emphasize this input here is not QCI. So it would be wrong to write QCI. That's completely wrong. And the reason is that what's incoming to the system right here, it's the same flow rate Q, but the concentration of salt is what the concentration of salt was over here at a time theta ago, right? So what this input really is Ci of t minus theta, right? Because it's this function here shifted to the right, right? It's delayed. Okay, so I can write that here. T minus theta, right? And so to explain that, write this down. The input to the system is Ci at a time. I won't decorate a time. It's T because that's confusing. At a time theta ago because of a time delay. Okay? So the true input to that system right at that boundary of the control volume is Ci of t minus theta, right? So it's old news. That concentration of salt has already been seen over here at time theta ago. And we can decorate this with stars to denote that we put this in deviation form if Ci is a function of time. So Ci equals Ci of t, right? That's your input. Okay, and your output is this, C, right? Because that implies C equals C of t, right? If the input concentration is changing, the output will as well. Right, and there are dynamics associated with that because it's mixing around in that tank and there's some holdup in the tank. So we can take the Laplace transform of this, and we get V S C star, right, equals Q. And now when we take the Laplace transform of this, we know what to do. It's Ci star, the input, but now we have a time delay. E to the minus S theta, right? So what we've done is we've taken the Laplace transform of a function, right, that's shifted to the right. And what we get is the Laplace transfer of that function without the shift times e to the minus S theta. And that's exactly what we have down here. We have the Laplace transform of the function without the shift times the time delay, e to the minus S theta. Okay, minus Q C star. And so Q here is constant, okay? Q constant. Okay, so what we can do is rearrange this and derive the transfer function. So G of S, which is the Laplace transform of the output here, C star of S, over the Laplace transform of the input here. And really this is the input that I've defined right here. This is the input. Input. That's our input, all right? This is equal to e to the minus S theta over V over QS plus 1. All right, and so this looks like a first order, and this is called first order plus time delay, okay? So now there's a time delay associated with that, and we'll study these systems a lot. So this is a transfer function of first order plus time delay, and these arise anytime when the input to the system is delayed, where there's a delay between the influence of the input on the output, okay? As is here, because the input takes a while to travel to the tank. Now, generally, they arise from ODEs that look like this, okay? So, as I said, right here, the input, the influence of the input, U star of t, is delayed by a time theta, and that could be from fluid flow. Okay? And anytime that happens, if you take the Laplace transform of this, right, you get tau s y star plus y star equals k u star, that's the Laplace transform of u star of t, and then you have the e to the minus s theta term which pops out. So then you get your y star over u star equals k over tau s plus 1 e to the minus s theta. Yeah. So that's where this transfer function here comes in. right? This is our transfer function right here. We've just sort of derived it. Yes. Yep, so that's our transfer function. Okay, and so we might be interested in what the impulse response of a first order plus time delay process is. And all it is the impulse response of a first order process, but delayed by theta units of time. All right, and so this here is the impulse response of a first order process delayed, shifted to the right by theta units. So how do we know this? So I'll go through one of these. Well, if you have an impulse input, that means that U star of S equals 1. Right? That's the Laplace transform of a Dirac delta function. And that implies that Y star is just a transfer function. So the transfer function is the impulse response, remember. Right? So that's Y star based on the transfer function. And now we want to invert that, right? And so again, what we'll do is we'll say, oh, well, this right here, this is some function f of s, right? And we know the inverse of this right? Oh, so we're doing an impulse response of magnitude m. So that's where the m comes from. So this is going to have an m here. And we know that the inverse of this is just an exponential. Km over tau e to the minus t over tau. And this is simply the impulse response of a first order process, right? If you remember that. So I'll say FO for first order. All right? And based on what we've shown, y star of t, if we invert this, right? L inverse. Then what we'll show is this is just f of t. So let me move this over so I can define this to be f of t. This is just f of t, but shifted to the right. E, and then I'll shift it to the right, so we'll put a t minus theta there over tau. And now again, this function here is 0 for t less than 0. And so to not pull over part of this function for when t is less than 0, what we need to do is multiply this by a step function, s of t minus theta, and that flattens it for t less than theta. And voila, we've just derived that the impulse response of a first order plus time delay process is the impulse of a first order process, but delayed by theta units of time. And I plotted it right here, right? So all we've done is shifted the impulse response by theta time units to the right. So this is the impulse response of a first order process, exactly the same shape, just shifted to the right. Which makes sense, right? If the input is delayed, then simply the output will be delayed by theta units as well, okay? And so similarly, if you have a step response, well, the step response of a first order plus time delay process is a step response of a first order process, but delayed by theta units of time. So again, here we are. This is theta, and this is the exact same shape as a first order step response. Exactly the same thing. It's just shifted to the right. It's delayed by theta units of time. Okay, so I also want to show you that time delays, we can approximate them as zeros or poles. There's many different ways of doing this, and this is totally an approximation. It will not, the math will not be faithful to the time delays if you do this, but it's often a reasonable approximation. So one thing you can do is approximate a time delay as a 0, or you can approximate as a pole, Or you can approximate it as a pole and a zero, okay? And the key lies in a Taylor expansion or a pod A approximate for poles and zeros. So if you want to approximate as all zeros, you can expand this e to the minus theta s term as a 1 minus theta s. And what you can see is that introduces a right half plane 0 at s equals 1 over theta, right? And remember, what right half plane zeros do is they slow down the response. And this is totally consistent with what a time delay does. It slows down the response, okay? So that should make you feel good that the zero approximation ends up slowing down the response as opposed to not having a time delay or a zero. However, this is of limited utility. We'll never do this because a physically realizable system cannot have more zeros than poles, and so we would end up with a system where you can see into the future if we didn't have many poles already. A more common one that we'll use is the all poles approximation. It's the exact same idea. All we do is note that, oh, this e to the minus theta s time delay term is the same as 1 over e to theta s. And then we Taylor expand that, okay? So this is the Taylor expansion of e to the theta s, the first order Taylor expansion. And what this does is introduce a pole, is a left half plane pole at s equals minus 1 over theta. All right? And one thing that's nice, this pole is in the left half plane, so it's a stable response mode. It's not going to destabilize your process. However, if theta is large, i.e. the time delay is large, then you're going to have a big time constant here, right? So this is like a time constant. And a big time constant, so theta plays a role of time constant. A big time constant means a slow response mode, and that makes sense. If you have a big time delay, your process will be slower to respond. So the other approximation you can make is called a pod A approximate. I encourage you to check these out. They're quite fun. And so this is the 1 pod A approximate of e to the minus theta s. And you can see on Wikipedia you get these by matching the function values in its derivative at an anchor point of 0 here. So you can derive this for fun at home. But what this does is it introduces a right half 0 and a left half plane pole. Okay, so it introduces both of these, both of which have the effect of slowing down the response. So if you introduce a time delay, you approximate as a pod A approximate, the time delay will essentially slow down your response in this approximation. So, for example, here's a first order plus time delay step response right here. That's this green one. So see how it's shifted to the right, it's just a step response. Now, if you approximate that time delay of theta with a 1-1 pod A approximate, the step response looks like is as follows. It's this blue line. So you see a little dip here that is spurious, but it actually follows quite closely, right? So that's what the approximation looks like, just to show you in terms of a step response. So these here are step responses. We're comparing step responses. Okay, and the last thing I want to show you is that we can work backwards and approximate a higher order transfer function with a time delay. And you might want to do that because lower order transfer functions are very convenient to analyze. We don't know how to analyze, for example, first over third order transfer functions, right? And the way that we can do this, and I'll illustrate it below, is just work backwards, right? So a 0, at s equals minus 1 over theta is approximately a time delay of theta, right? And a left half plane pole at s equals minus 1 over theta is approximately a time delay of theta, right? And that comes from these two Taylor expansions, basically, right? So anytime you see these terms, you can approximate the zeros and poles respectively as time delays. Oh, I see a mistake. So this should not be there, but yeah, I'll fix that in the notes. Yeah. Sorry about that. Okay. So let's put this to use now. So you see here, this is a first over third order transfer function, let's approximate as first order plus time delay. We'll do the 0 first. So here's your 0, right? I'll use the same color. So the 0 minus 0.1s plus 1. If we look at this Taylor expansion, this is approximately a time delay of 0.1, right? And now if we need to approximate two of the poles as time delays. The question is, which poles do we choose? And the answer is that we need to choose the fast response modes to approximate. And those are the smaller time constants. Whereas we want to retain the dominant time constant, because we want those slower order dynamics to be the main contribution of the transfer function's dynamics. And then the fast response modes, you can approximate them well with a sharp time delay. And that's sort of intuitive because we know that Taylor expansions, like this Taylor expansion here, it gets better if theta is small, right? And those are fast time dynamics. Theta is small, time constant small, fast. So basically, mathematically, this transfer function should be the first one we should approximate with a Taylor expansion because it's going to be the best approximation. So 0.5s plus 1. This is approximately e to the 0.5s, right? Okay. Another way to say this is that if we do the inverse, 1 over 0.5s, you get the same thing, is approximately e to the minus 0.5s. Okay, so let's do the other. Let's make this one red. So now we should approximate this pole. 1 over 3s plus 1. Well, this is approximately e to the minus 3s, right? A time delay of 3. And if you combine all of those, so g of s is approximately 13 over 5s plus 1, e to the, and you add up all these time delays and you get 3.6. 3.6s, all right? And that is first order plus time delay. All right, so the art here is in choosing and knowing which poles to approximate with a time delay, okay? So if you choose 5s plus 1, that will be a worse approximation than if we had left it there. That's really the only art here. Otherwise, it's sort of straightforward. And what's nice is the first order plus time delay transfer function, we can analyze this in our sleep, very easy. Whereas the one here, I have no idea when I look at that what the dynamics will be like. So this is very helpful. And just to show you, I ran a simulation here. So this is the step response of that transfer function g of s, the blue one. You know that's okay. That's the first order plus time delay one because there's the time step. So the g of s transfer function, its response is the green one, right? Right here, this green one right here. Those are the true process dynamics. And then we approximate with this first order plus time delay, and this is how it approximates it. Not bad, right? Although you do see this region here where it's exactly 0 until a certain time, even though the true response is non-zero. So that's a little bit unsettling. But overall, it's a good approximation, especially at later times.